Dr. Fizz with simple combinatorics. You have 5 people in a family and 2 tickets to the movies. How many ways can 2 people from that family go to the movies? Well, there's 5 ways to give the ticket out to the first person that's going to go. That person gets a ticket, steps to the side, and there are 4 ways to give the second ticket out. So there's 20 ways to give those tickets out. However, it doesn't matter who got their ticket first. So we divide by 2. So 20 divided by 2 is 10. And that gives us our answer. It doesn't matter who gets into the car first. So we want to divide by 2. We want to also write these as factorials, so we write 5 factorial over 3 factorial to kill the 3, 2, 1, and we include the 1 here so that we think of this as 2 factorial. This is a beautiful symmetric form where you can think of this as n1 being the state of going to the movies and n2 the state of staying at home. And we can add in third state an n3 factorial in the denominator, and then a capital N would be n1 plus n2 plus n3. Very important in physics to have it in this symmetric way so that you can think of particles in different energy states. This relates to the binomial expansion, where you have a plus b, the quantity to the nth power. You write a to the nth first, b to the 0th, and each term here, a knocks down by 1 power, and b increases by 1 power. Think of this as the 0th term, the first term, the second term, where the term is key to the exponent for the b. And the nth term is b to the nth, and then a would be to the 0th power. Notice that the sum of the exponents, when you look at the a and the b, always give you n. Here's n, because b had a 0, n plus 0. Here's n minus 1 plus 1, and n minus 2 plus 2. So these all add up to n. The coefficients can be thought of in a neat way. By the way, the 0th one and the last one have 1. When you come here to the first term, you write n and you divide by 1. I do that because I want to think of writing down the number of numbers that correspond to that exponent, which is 1. So I write one number, but I count backwards and I count forward. Backwards in the numerator, forward in the denominator. So for the second term, b squared term, I have 2 numbers in the numerator, n and then n minus 1, because I'm counting backwards from n, and here I count up 1 times 2. If we go to the third term, we would have b cubed over, that would then count backwards, so you have 3 numbers, n minus 1 and minus 2, and 1, 2, 3. Notice that the last number here, 3, is off by 1 when you look at the top last one. So here 2 went with that minus 1, 1 goes at the minus 0. So you can think of the r here being 1 greater than this. So in other words, we're going to subtract 1 less than the r. So if the r is 3, we subtract 2. If the r is 2, we subtract 1. So if you subtract 1 less than the r, you're subtracting the quantity r minus 1. So you get then a minus r, and a minus minus on the 1 gives you a plus 1. And this is the general formula and definition how this works. You can think of this as how many ways can you pick fruit, n pieces of fruit from apples and bananas. Now, how many ways can you pick all of them to be apples? In other words, no bananas. Well, 1 way, just pick all the apples. How many ways can you pick 1 banana and the rest being apples? Well, there's n ways to pick one of the bananas. You can think of a plus b, times a plus b, times a plus b, times a plus b, times a plus b, on and on. So I can pick from any of those parentheses, any of those terms in parentheses, and there's n of them, so I can pick b n different ways, and then I'm stuck with all the apples. How many ways can I pick 2 bananas? Well, the first one n ways, and then like the family. Then how many are left? Well, there's n minus 1 ways to give the ticket, or to pick the second one, and then I count upwards 1 times 2, and divide it by 2 so I don't have the double counting. And that can get you all of these coefficients. Look at the last one. You would count backwards n all the way down to 1, and count upwards 1 all the way up to n, and that would be 1. That would be 1, a coefficient of 1. And here for the 0th term, we don't really count at all. We just put a 1 down. It's a 0th term. the Pascal triangle is a nice way to see this. Very beautiful result where you can look at this as if n is equal to 0, then you have the answer is 1, so you just have a 1 here. And if n is 1, then you find a plus b. So there's a plus b. These are the coefficients. If n is 2, you have a squared plus 2ab plus b squared. And if a is cubed, you have then the 1, with those 3's in there. And you can think of this as a 0th power, first, second, third, fourth, fifth, sixth, and here's a 7th power. And you can think of the terms in the expansion, and you get more and more as you get higher powers. You have 0, 1, 2, 3. This would be 0 because the b would be the 0th power. That's how we tag that. And this is b to the first power. So you can look at the coefficient here, 21, as going with the b squared in your expansion. So if we plug the numbers in here, n is 7 and r is 2, we would have 7 factorial over 2 factorial, and this would be a 5 factorial, would give 7 times 6 divided by 2 is 7 times 3 is the 21. And another neat thing is that you can get all these numbers from their parents. All right. Now this is of course the first one. So but you have here 2 has parents, 1 plus 1 is 2. 10 has parents, 6 plus 4 is 10. I'm just jumping around anywhere I want to go. 3 is 1 plus 2 are the parents, give 3. Hey, 15, 5 plus 10. So the parents are on the slant on the generation above you. Here 21 would be the sum of 15 and 6. That's amazing how that works and how it all ties together.